In this video, we'll be finding inverse functions given a function. Since a function must be one-to-one to be eligible to have an inverse, the first thing we need to do is verify that the given function is one-to-one. We'll do this by drawing a picture of the graph and then seeing whether it passes both the vertical and horizontal line tests. When you're drawing this graph, you want to draw it pretty accurately, just because we're going to be using the domain and range of the graph we draw to identify the domain and range of our inverse function. Once you've determined that the function is one-to-one, we'll proceed with actually finding the inverse function. We'll start by taking it out of function notation by letting y be equal to f of x. Next, we'll interchange the x and the y, just as we did when we were finding inverse functions of both graphs and ordered pairs. Next, we'll solve for y, and then lastly, we'll put it back into function notation by replacing the y with f inverse of x. Let's find the inverse of each given function, and we'll state the domain and range of the inverse function. So the first thing to do is to determine whether this is a one-to-one function. We'll draw a graph of f of x. This is a line with a y-intercept of 0, 3, and a slope of positive 7. When we draw this in, we get this diagonal line. Is this a one-to-one function? Does it pass both the horizontal and vertical line test? Yes, it does. So this is one-to-one. That means that we can proceed with finding the inverse function. We're starting with f of x equals 7x minus 3. The first thing we'll do is take it out of function notation. So we're going to replace that f of x with y. Next, we want to interchange x and y. So everywhere there's an x, put a y, and everywhere there's a y, put an x. Now we want to solve for y. We'll start by adding 3 to both sides, and then dividing both sides by 7. We get y to be equal to x plus 3 over 7. That is our inverse function, but now we need to put it back in function notation and say that f inverse of x is equal to x plus 3 over 7. We also need to state the domain and the range of the inverse function. We're going to use the fact that the domain of the inverse function is the range of the original, and the range of the inverse function is the domain of the original function. So the domain of our inverse function, well, that's the same as the range of our original. So let's just take a look at the graph we drew and state the range. We have an arrow pointing down and an arrow pointing up with no breaks in the middle. That makes it negative infinity to positive infinity. And then the range of our inverse function, well, that's the same as the domain of our original function. So let's look for the domain of the graph we drew. Again, we have an arrow to the left and an arrow to the right with no breaks in between, which gives us a domain of negative infinity to positive infinity. So both the domain and range of our inverse function is negative infinity to positive infinity. Let's try another one. This time we want to find the inverse of g of x equals the square root of x minus 1. The first thing we need to do is verify that this is a one-to-one function. We'll draw a picture to make that determination. As mentioned before, we want to draw a pretty accurate graph just because we're going to need the graph for the domain and the range of the inverse function if it exists. So this g of x, that's our square root function, but it's been shifted to the right 1 unit. So it looks like this. We don't need every point on the graph. We just really need the starting point and the ending point. We'll use the vertical and horizontal line test to determine whether or not this is a one-to-one function. You'll notice that this passes both tests, so this is indeed a one-to-one function. That means we should be able to find the inverse. So we're starting with g of x equals the square root of x minus 1. The first thing to do is to take it out of function notation by replacing the g of x with y. Next, we want to interchange x and y. This becomes x equals the square root of y minus 1. Now we want to solve for y. Since y is underneath of the square root, this is a square root function that we're solving for, square root equation. So we'll start by squaring both sides. This gives us x squared is equal to y minus 1. And then to solve for y, we'll add 1 to both sides, giving us y equals x squared plus 1. This is our inverse function, but now we need to write it in function notation. G inverse of x is equal to x squared plus 1. Next, we want to find the domain and the range of this inverse function. The domain of g inverse is the same as the range of g. We'll take a look at the picture of our graph above of g to help us get this domain. So the domain of g inverse is the range of g, and the range of that graph is including 0 to positive infinity. Now the range of our inverse function, well, that's the same as the domain of the original. So we can take a look at the graph we drew and state the domain, and that'll give us the range of the inverse function. So our x values start and include 1 and go to positive infinity. The domain of g inverse is 0 to infinity, while the range of g inverse is 1 to infinity. Now, you may have noticed that g inverse of x is equal to x squared plus 1, which is a parabola. In fact, this is a parabola that's been shifted up 1 unit. Well, inverse functions are supposed to be one-to-one, but this clearly is not a one-to-one function because it fails the horizontal line test. But note that we have a domain restriction. It says that the domain of g inverse is only from 0 to infinity. So we're only looking at this half of the parabola. We're not looking at the left side at all. It's outside the domain. And since we're only looking at half of the parabola, it does pass the horizontal line test. Let's look at one more. F of x equals 4 over x minus 1. We want to start by determining whether or not this is a one-to-one function. Well, this is our rational function that's been shifted to the right one and vertically expanded by 4. There's going to be a vertical asymptote at x equals 1. Remember, we set our denominator equal to 0, and that's where our vertical asymptotes are. This is also going to have a horizontal asymptote at y equals 0, since the degree of the denominator is greater than the degree of the numerator. And we draw in our rational function. Does this pass both the vertical and horizontal line test? Sure does. Since this is 1 to 1, we should be able to find the inverse. So we're starting with f of x equals 4 over x minus 1. We'll take it out of function notation by replacing the f of x with y. Next, we'll interchange x and y. It gives us x is equal to 4 over y minus 1. And now we need to solve for y. The variable we're solving for is in the denominator, so our number one priority is to get it out of the denominator. You can think of this two different ways to accomplish this. You can either look at this as a rational equation and multiply both sides by the LCD of y minus 1, or you can note that this is a proportion and we can cross multiply when we have a proportion. I cross multiply whenever possible. So that's going to give us x times the quantity y minus 1 is equal to 4. And now we solve for y. How you solve this, really you have two options. I'll do them both ways, and then you can choose the one that makes most sense for you. Now, I got to get rid of this x, so my first option is just to right away divide both sides by x, leaving us with y minus 1 equals 4 over x. And then we add 1 to both sides, giving us y equals 4 over x plus 1. We'll put it back in our function notation. So f inverse of x is equal to 4 over x plus 1. Our other option for solving would have been to distribute the x. That'll give us xy minus x equals 4. Solving for y, we can add x to both sides and then divide both sides by x. This leaves us with y equals x plus 4 over x. There's our inverse function, which we will write in inverse notation. F inverse of x equals x plus 4 all over x. These are equivalent answers. If when you divided both sides by x, if you'd have done the terms individually, it would have simplified to be 1 plus 4 over x. So they're the same, whichever solving technique you feel more comfortable with. That's the one I want you to use. We now need to state the domain and range of our inverse function. We're going to use the graph that we drew originally to help us with this. We know that the domain of the inverse function is the range of the original, so we'll take a look at our graph and state the range. Now, we have a horizontal asymptote at y equals 0, so our range is going to include anything except where that asymptote is. So we'll have from negative infinity to 0, and then from 0 to positive infinity. The range of our inverse function, well, that's the same as the domain of our original. So we'll look at our graph and state the domain of that graph. We notice that there is a vertical asymptote at x equals 1. So the domain of that function will include everything except 1. That'll be negative infinity to 1, and then from 1 to infinity. So the domain of f inverse is a negative infinity to 0, 0 to infinity, and the range of f inverse is negative infinity to 1, 1 to infinity. In our last example here, we're going to step it up a little bit. So given h of x equals x squared plus 6x minus 4, we want to determine what domain restriction would have to be set so that h inverse could be found. Because we know right now this is not a one-to-one function because the graph is a parabola and it fails the horizontal line test. So once we determine what that domain restriction would be, then we want to find the inverse function with that determined restriction. Oh, so we know that this is going to be a parabola facing up. And we need a one-to-one section of this graph. And we want the biggest one-to-one section possible. So basically, it needs to pass the horizontal line test, which means that we need one side of the parabola, like from the vertex over. So what we need to do is find the vertex of our quadratic here, and that will tell us the domain restriction, and then from there we can find our inverse function. Remember to find the vertex, the x-coordinate of the vertex will be negative b divided by 2a. That's negative 6 over 2 times 1. The x-coordinate of our vertex will be 3. Negative 3. So that means that our axis of symmetry is at x equals negative 3. We don't actually need to find the y-coordinate of the vertex. We just need to know like where the split is, and that split's happening at x equals negative 3. So our restricted domain would be from negative infinity to negative 3, and we can include that 3, or it would be from the negative 3 to positive infinity. So choose one, don't choose them both, you're just going to choose one. Alright, so now that we know what our domain restriction is, let's go about actually finding the inverse of our function here. We've determined the one-to-one section, so now we want to take it out of function notation by replacing our h of x with y. Next, we will interchange x and y. And then we need to solve for y. This problem is more challenging because we're actually going to have to complete the square to be able to solve for y. I'll get myself prepared for completing the square. So our y terms on one side, our constant and x term on the other. This becomes x plus 4. I'm going to leave a little space equals y squared plus 6y. To complete the square, we take our b value, divide it by 2, and square it. That'll give us our perfect square trinomial. So 6 divided by 2 squared. We get 9. So we're going to add 9 to both sides. Our perfect square trinomial always factors into the form y plus b divided by 2 squared. On the left, this is x plus 13. On the right, factors into y plus 3, quantity squared. Now we're going to take the square root of both sides. Since we're doing square root property, we need the plus or minus. So plus or minus the square root of x plus 13 equals y plus 3. Okay, so this plus or minus has emerged because we did square root property. You only want one of them, and the one you want is the one that should be corresponding with your domain. Oh, I would choose the positive side for my domain, so I'm going to choose the plus or minus and throw out the negative down here. So that brings us to y plus 3 equals positive square root of x plus 13. And now solving for y equals the square root of x plus 13 minus 3. And then the last thing we want to do is put that back into proper function notation. H inverse of x is equal to the square root of x plus 13 minus 3.